Also, I wanted to say that I want the session, since it's kind of like a long session, and I've been doing also other long talks, and if I'm the only one talking, and then it becomes a bit boring. So whenever people have any questions, I'm fine with asking questions at the end, which is the usual way to do it. But I'm also very fine to, it's very good for me to be interrupted and ask any questions, because there's a lot of material, and there might be things that then people might forget to ask. So feel free to interrupt me if there's anything that is not clear, or you would like to have more kind of like more information about.
Definitely, I think the audience would love that. Definitely, yeah, sure. We'll also convey that once just before you start the session, so that I'll just convey to the audience. Yeah. Yeah,
sure.
So I was also curious about how is entrepreneurship and neurotech startups in UK? I also saw that you're also just entering into that domain, your collaboration with Tech Superconnectors. So how is you break that down?
So it's actually in Europe in general, things are changing quite quickly, and it used to be a mainly US driven type of field. So because there's a lot of more money in the United States, and there's a lot going on there as well. The main technologies that I will be talking about today, they're actually mainly from the United States, but there's a lot happening in Europe, and there are startups coming out also in the UK. There's quite a few interesting ones, both in kind of like neurotech, but also medical devices in general, medical technologies in general. So, but yeah, more recently, I've been transitioning more into the translational and entrepreneurial world of neurotechnologies, because that fascinates me. Because sometimes I feel that if technologies stay within academia and they don't move out of academia to become actual devices to be used by people, there's no point of doing it. Although there's a lot going on into research tools to help actually neuroscientists to learn more about the brain. So of course, those technologies are useful as well, even if they don't translate directly to medical devices for clinics.
I mean, that's one thing that I also like. It was really awesome to see that you're getting into that translation research, because I think that's totally needed at this moment, because there's a lot of technologies coming up and research is going on. That's why we are trying to do that in India. And I think platform like NeuroTechX is really helping us to get everybody in a single platform. We're trying to get nations, researchers and technologists and even students onto a single platform where we can sort of interact and sort of come up with new ideas and products that can really impact humanity. So.
So yeah, it makes sense actually. NeuroTechX is a very good platform. It has a bit of everything, both educational and also trying to develop technologies, trying to create communities, and so it's very good. It's very good that it's increasing. Also in the UK now, it's increasing as well, the NeuroTechX community, from what I'm seeing, which is good to know. Also, like, still Europe and US, United States and Canada are the biggest cores, but Europe and India are coming out.
I think Europe has like seen a lot of startups recently in the space of neurotech and research.
Definitely.
Yeah, I think that's interesting, and it's all good for the field. I think it's really growing.
Exactly, and you know what? It's also a matter of investment. So when it has been quite slow in Europe, also because the investment landscape is a bit different from the United States, and there's not that much kind of like risk that venture capitalists or angel investors are taking for these type of technologies, because venture capitals are looking for a short-term investment, a short-term return of their investment, which is like 3 to 5 years. But neurotech cannot be in a return in 3 to 5 years. I mean, if you're developing a medical device that is going to be implanted into the brain, it will take longer than that. And so, but now it's changing, because the Europe investment landscape is seeing what's happening in the United States, which these investments are happening, and they're seeing a lot of companies also being acquired by the big established companies, and that's also the return on investment, having an exit to be acquired by someone else. And so that's very interesting for investors also in Europe. And so now things are coming up, and a lot of investment is happening. There was the recent big investment, I think around 17 million euros, I think, from the Brain Neuroelectronics, which is a company that was formed in Barcelona in Spain.
Oh, okay.
And so that had quite an interesting investment. They're developing graphene technologies. They're still early stage, but it's highly scalable and it will become bigger and bigger. But anyway, I mean, we can talk about this for hours.
Okay, yeah, okay, fine. Yeah, I think yeah, that's interesting. Okay, I think yeah, it's been 7:05. So with no more waiting, since you mentioned, I'll just give the platform to you to give an introduction about yourself in order to start. I think first of all, welcome to NTX India, all the attendees. I think people who have attended first time. This is a forum where we sort of conduct events, workshops, and a lot of interesting activities where sort of we engage in discussions surrounding neurotech and neuroscience. So for this session, we have one wonderful speaker with us, Dorian. He's from London, and he's doing some wonderful works in implantable neural interfaces. So with no more waiting, we'd get Dorian for his session. And just one information, you can, if you have any queries in the middle, you can definitely interrupt and ask Dorian during the session also. I think hopeful for a very exciting session, Dorian. Yeah, stage is yours.
Thank you very much. I'll try to share. Let me know when things are up.
Yeah, I think it's visible for all of us. Yeah.
Okay, give me just 1 second. So I set this thing up here. So I move Zoom from the way. Okay, here I am. Thanks a lot for the invitation. It's really a pleasure for me to be here and to talk about what technology we're developing at Imperial College London within the next generation neural interfaces lab, but also to give an overview of implantable neural interfaces. In fact, my talk today will be divided in 2 parts. The first part will be an introduction to implantable neural interfaces, where we are now, where we're heading, and what the challenges as well are to create the next generation of these type of technologies. And then the second part will be an introduction to my research group at Imperial College London and to what we're developing in terms of technologies, our philosophy, and I will focus more on 2 specific projects, which are the CANDO project and the NGINI project, and we'll go a bit more into details about that. If you have any question, as mentioned before, please feel free to interrupt me. And also, if you have more specific questions, technical questions regarding the projects, I will then head you to the publication that we have in the field if I cannot answer immediately to the question. But first, I wanted just to give a very quick introduction about myself. I'm a researcher at the Imperial College London, which is a university in the United Kingdom, specifically in London. This is a picture of our Queen Tower in the beautiful South Kensington campus in central London. At Imperial College London, I'm part of the Center for Bioinspired Technology, in which we're developing technologies that are inspired from nature, and also part of the next generation neural interfaces lab, which is developing implantable technologies, and also not just implantable technology, but neural interfaces and new technologies. And I wanted also to mention that for the past year, I've been part of the MedTech Superconnector, which is an accelerating program to help translate medical technologies and research into medical technologies that then are being used in clinics. And very recently, I have also become an enterprise fellow of the Royal Academy of Engineering, which will allow me to then focus on one of these projects that we'll be talking about next. And I've been also part of the IEEE. I've been an IEEE member for 7 years, and I've been kind of like having different roles in different workshops and conferences. So before starting talking about neural interfaces, I want to start talking about science fiction, which where neural interfaces have come. And so if you are old enough to remember the Matrix movie, there's the protagonist who is Neo, who gets this scary looking plug shoved into his brain in order to then jump into the Matrix and to control his virtual body in there, and also learn very quickly Kung Fu or other type of solutions. Then there has been more recently the Avatar movie, which the protagonist, Jake Sully, sits into this bed-like fMRI-like technology, and with just the power of his mind, he's able then to communicate or control a humanoid avatar and move it with just the power of his brain. And very recently, then there's been the Black Mirror series, in which people are able to record their memories and to play them back, and to also play video games with their brains. But what of this is science fiction, and what is this is science fact? So more recently, you might have heard of the different technologies that are coming up, but the media always tries to pick and choose the quotes from sci-fi, giving a sci-fi spin in terms of neurotechnology development. And you might have heard of and seen headlines such as downloading memories and addiction implants, merging human and machine, and the AI doctor that can control you, and then trying to hack the brain. But I wanted to kind of like demystify also these headlines and try to give a better understanding of what neural interfaces are, more specifically of what implantable neural interfaces are. So let's start with the first question: what are neural interfaces? So there has been a lot of definitions, but the one that I found to be the most correct for me is that neural interfaces are direct connections of technical components to the brain or the nervous system. And they have different capabilities. On one side, they are able to restore lost functions of our body, or also to enhance them by connecting to the nervous system of the brain. And on the other side, they are able then in future to transform medicine and change how we interact with each other and how we interact with technology. So to give a general definition of the neural interfacing concept, we can think of it as a processor that somehow connects to the nervous system, in this case, the brain. It can connect in two ways. So from one side, it can connect by having a sensory interface that can measure, for example, sound or images, and then can be sent to the processor, which will then stimulate the nervous system in order for the person to have that sensation of sensory sensation, such as, for example, the cochlear implants or retinal prosthesis. On the other side, the other way is to record directly from the nervous system, and with the data that is processed by the processor, then you can control an interface, a motor interface, something that, for example, can move a wheelchair, a robotic arm, or even a cursor on the screen. And so we know now what neural interfaces are in general, but what the real neural interfaces are and how they look like. To understand that, I think we need to diversify in two directions. On one side, the wearable technologies, on the other side, the implantable technologies, which I'll be focusing more during this talk. The neural interfaces on the left side are wearables, such as the EEG headsets, which are recording the brain signals from outside, and that can be both industry-driven, so more commercial, and on the other side can be more medical, as the picture in here. And there are also other ways to connect with the nervous system, for example, with the TENS machine, and try to connect with the peripheral nervous system, the peripheral nerves, and also the Control Labs, which was recently also acquired by Facebook, is a company that is developing something that you can wear on your wrist that can measure electrical activity of the nerves that are then connected to the brain, and try to understand what you want to do, what you want to move by measuring that. On the other side, there are implantable devices which have been used in medical applications, or to record signals from the brain, or even to stimulate and interact with the spinal cord, for example, for chronic pain. And on the right side, on the bottom here, you can see a cochlear implant, which is one of the most famous and successful devices. I wanted to give also a distinction because we often hear brain-machine interfaces, brain-computer interfaces, neural interfaces. So what are they? How are they defined? And in my opinion, brain-machine interfaces and brain-computer interfaces are a subgroup of neural interfaces. And these are specifically to decode useful information from the brain and use that information to communicate, control an external device. As we were talking earlier about brain-machine interfaces to control a wheelchair or a robotic arm. Two examples which are important also to define this are one, which is the BrainGate brain-machine interface that is an implantable device that can allow people to move a cursor on the screen or to move a robotic arm. These technologies are usually defined as brain-machine interfaces as they are implantable. And what I've noticed as well is the brain-computer interfaces are more wearable type of technologies, such as the one that you can see on the right, which is done at EPFL in Switzerland, and helps people that are that don't have mobility of their legs to move than a wheelchair. They don't have mobility because they might have had a spinal cord injury. And so these two distinctions are brain-computer interfaces are more for wearable devices and brain-machine interfaces are more for implantable devices. And they are both used to detect signals to be used then to control the external devices. So, but when do we use implantables? When do you use wearables? There's always been this kind of debate in this field, but it's not much of a debate because there are applications in which implantable devices are useful for and applications in which wearable devices are useful for. And so it depends what you wanted to use them for. And so here I listed, I won't go into details of all these functions, but I've listed some of the characteristics that these devices might have. And when it's good to use one of the technologies, such as wearables, or when it's good to use implantable technologies. And as you can see here, there are characteristics which are better for implantables and characteristics which are better for wearables, such as, for example, risk. If you have an implantable device, the risk is higher, also for surgery, and if you have a wearable device, the risk is lower. So focusing on implantable neural interfaces, I wanted to start from two medical successes for the past 2-3 decades, actually. So on one side, we have the brain stimulator that has been used for Parkinson's disease or essential tremor. And it is an implantable device that sits in the chest, but it has a wire that connects to the brain, connects actually to the deeper regions of the brain, where the electrodes stimulate the part of the brain to stop the tremor and to stop the movement that is specific to Parkinson's. But there are about 300,000 people in the world actually having this implant today. The other one, which is probably the most famous one, is a cochlear implant, which some people might not think of it as an implantable medical device for neural connection, but it actually is, because it connects, the electrodes connect to the cochlea, which is directly in contact with the nerve, auditory nerve that goes to the auditory cortex. And so by doing the stimulation of the cochlea, you can give back then sound to people that are deaf and they cannot hear anymore. So from these two medical successes, there have been other medical applications in the past decade or so, which have helped with other conditions. On one side, there are diagnostic technologies, which are, for example, technologies to measure neural activity to detect epilepsy and to, for example, detect seizure development in epilepsy patients. Technologies, for example, for sleep disorders, such as ECOG electrodes that are implanted directly into the brain. So there have been technologies that are implanted into the chest and they connect to the nervous system, or they're implanted directly into the brain for these disorders. On the other side, there are assistive devices. So devices that are, on one hand, trying to record motor or motor signals from the brain, as we were speaking earlier, and to use that in brain-machine interface applications, then to control the robotic arms or wheelchairs. Others are for example, the retina prosthesis to give sight back to people that cannot see. Others are connected to the spinal cord to stimulate for pain relief. And as we mentioned, the DBS therapy for Parkinson's and essential tremor, but not only, also for epilepsy. So there's two distinctions of diagnostic technologies and assistive technologies. But what are the state-of-the-art implantable technologies today? So on one side, we have the BrainGate implant that I showed also earlier, The implant is actually developed by a company called BlackRock Microsystems, and it allows to connect with what is called UTA ray. It allows to connect with the motor cortex, which is a specific part of the brain that is activated when you have the intention to move one of your arms or your body. And these technologies are implantable, and they've been very helpful. However, the transfer rate is quite slow because they're connecting to a very tiny part of the brain, and it has different challenges, such as the fact that it is not fully implantable because there's a part that's coming out of the brain and connecting to a cable, and also it has a need for calibration quite often. Another type of technology is active implantable medical devices, such as the deep brain stimulator or cochlear implants, as we discussed earlier. These are established technologies, and they're used also, these type of electrodes are used also for research platforms. However, they are very difficult to scale because these electrodes have very few, these implants have very few electrodes, so there's not that many channels to interact with the neural system. On the other side, there are research tools that are being developed, such as the NeuroPixel probes. These have a very high number of electrodes. They have a very good manufacturability and a very low cost. Good also in terms of scalability. However, these are technologies that are not always fully biocompatible, and so to make them biocompatible, to make them to stay in the brain or in the body for a long term, a lot of post-processing has to be fabrication has to be done with them. I can go on and talk about all the different implantable technologies, but I would highly suggest for who's interested to go to the iHuman report that we also actually contributed in writing a couple of years ago, in which there's a summary of all the different technologies that I mentioned, plus others, as you can see here in this slide. But what are the technical challenges to go from where we are now to the next generation of implantable neurotechnologies? I have identified here a few of them, which are interacting with each other. On one side, we have spatial resolution, so we want to have as much resolution as possible to understand more what's happening in the brain. On the other side, there's invasiveness, so we want to reduce the invasiveness. Although we're talking about implantable technologies, invasiveness in implantable is not always correlated, so it could be also something that is invasive, but it is implantable, but people don't feel as an invasive technology. And the neural interfaces side, so the more the bigger the interface is, and the worse is for the user, for the patient, for example. On the other side, we want to make also them scalable. So in order to increase the amount of these interfaces, in order to be able to monitor from different parts of the brain and to have, for example, a better coverage of the brain. However, these challenges come also with problems in terms of power efficiency. If you want to have something small, how do you power them up? How you make sure that they are powered for a long time? And also in terms of signal integrity, you want the signals that you're recording to be kind of like to have a good signal for long term and to have more information. So the first challenge is this resolution versus invasiveness. So we have seen the different type of technologies out there, for example, the EEG, which are wearable, then we have ECOG arrays, we have microelectrode arrays, which are local field potential, or spikes, which are implanted into the brain. And so the more invasive we go, the more the signal quality increases. The more we are out of the brain, then the more noise we have, so the signal will degrade. And so invasive electronics, such as the penetrating electrodes that I spoke, they can cover, they don't have a very large cover, but they have a very small pitch, and so they can record specific from a specific part of the brain. Minimally invasive, such as ECOG electrodes, they can have wider coverage, but the signal quality then is less because it's on the surface of the brain. And then the EEG, which are wearable, will have a very good coverage, and it's not invasive, but the resolution is not that high. Another challenge is scalability versus the device size. So what we have seen in the past decades is the Moore law of neuroscience. So there has been an exponential increase of the amount of electrodes and implanted electrodes in a single interface. And so the more electrode you have, the better the performance is, and the higher the transfer rate is. Sometimes the same electrode is recording probably the same signal in terms of information. However, having two electrodes to record the same signal is better because you have redundancy. And so if one electrode doesn't work, then you have the other one that is working fine. And on one side, we have implantable BMIs, which are high density probes, which we have this, this approach of increasing the density of the probes, increasing the number of channels for each probe. On the other side, we have a different approach, which is trying to increase the number of interfaces with a few electrodes, but more interfaces distributed all over the brain, for example. And the comparison with wearable brain-machine interfaces that the resolution is higher with this type of technology, and the wearable technologies don't have the same resolution as we discussed earlier. I introduced earlier the signal integrity issue. So when you have an implantable device inserted into the body, many things can happen to the device. Ideally, you have, as you can see in the central picture here, you have a technology which is recording from few or many neurons. However, this technology can stop working for many reasons. On one side, you have the biological failure, which you will have a reaction from your body, which is called the foreign body reaction, to an implant. And so the electrode will be covered with scarring tissue, which will not allow them to have a good signal. And on the other side, will also create damage on the device itself. Then you have material failure. So the material that you're using, although it might be biocompatible, that can fail, so that can open and that can make then the device which is inside, which is not biocompatible, they can make it in contact with the tissue and creating then a problem. And there can be also mechanical failures. If you have an implant inside of your body, they can move and they can break, of course, as well. And for then comparing to wearable devices, non-invasive electrodes, you don't have these type of problems. On the other side, you don't have either repeatability. So if you're placing a cap with electrodes and you remove it and you place it again, it will never be in the same exact position as it was before. So you have this calibration stage in which you have to understand to place it in a certain way that the signal that you're recording is the signal that you want. And also the signal to noise ratio, as we mentioned earlier, it's not good because you don't have the same contact that you might have with an implantable device. Another issue is power efficiency. Not an issue, is another challenge in moving to the next stage of implantable neural interfaces. And so power, the more channels you have, so the more electrodes you have, the more power you would need, of course, to record from those electrodes. So the minimal power requirements is very important. While on the other side, you want to minimize and to have multiple interfaces and multiple implants, this will increase the power that you require for that. And also another problem related to power is that you have to provide this power inside of your body. And when you have something outside of your body, then you just power it up with cables. But when it's inside of your body, you need a wireless way to then power up your system. It can be with a battery, which is not a rechargeable battery, for example, or with a rechargeable battery, or which has still an energy source which is implanted into your body, but it is a smaller amount of energy that is rechargeable with an external device. Or you can have also a system which doesn't have any energy source inside, but then uses an external system to provide the power. And it's very important for medical technologies to consider that the amount of power that goes inside, and also compared to the amount of temperature that then it's raised, because it has to be below a certain amount of degrees. With challenges, though, come also opportunities with this type of technologies. We have seen in the past decade many wearable technologies being presented, introduced, some as generic platforms such as the Microsystem, or for meditation such as Muse or Wearable, which is also changing to meditation as well, or the Dream cap, which helps for sleep monitoring. This approach has helped them to translate and to create this type of applications as well for implantable devices. And the main technology that is out there today that has as a goal a consumer application is the Neuralink technology from Elon Musk. And this is the ultimate goal, is to create this interaction between human brain and humanity with artificial intelligence. And what they want to do at Neuralink is to create this implantable device that then you can control directly with your phone and interact with the world in a totally different way. Another opportunity is to look at the form factors that have been used in the past and what form factors or concepts are going to be used in the future. And so what we have today is the Utah arrays, for example, from the BrainGate consortium and BrainGate project mentioned earlier. And these are very tiny electrodes which are implanted to the brain. However, they have cables that are coming outside of the body. Now, actually, they have also released one of their versions, which is actually wireless as well. And the other way is through deep brain stimulators with electrodes which are implanted deep in the brain, and they have a cable coming to the chest. However, if you want to see what's the future going to look like, we need to see what type of other technologies are there. Oh, actually, I have some pictures of the electrons. Sorry. And so the future, what they will look like tomorrow are technologies such as the Neuralink one, which uses microwires that are thousands of microwires that are implanted into the brain. Another one is the technology from Stentrod, Synchron, which uses a Stentrod, which is a catheter for the brain, which connects directly to the to the brain in an indirect way, not on the tissue, on the brain tissue, but through the veins. Another approach is the NeuroTechX approach, so to have multiple electrodes on a probe that then is inserted into the brain. It can go different depths, and you can measure or interact with the brain at different depths of the cortex or even deeper. Another one is to have a single interface, but with very, very tiny and multiple electrodes similar to the Neuralink one, and this is done by Paradromics. Or the distributed approach, so to have tiny devices which have few electrodes. However, there are many, and they're distributed on the brain or the nervous system. Another opportunity is to have brain-machine interfaces that connect not with just the motor cortex. So what we have seen so far is many of these brain-machine interfaces are connected and interacting with the motor cortex, which is the part of the brain that activates when you have an intention to move or you want to move something. And so, however, that's a low-level connection, and it's a low bandwidth connection actually, which gives you the possibility to have not many degrees of freedom in terms of control, and you will never have very high data rates that can come out from the recording the motor cortex. Another approach, which has been more recently, is to record and interact with the brain in different parts of the brain. So not just in the motor cortex, but for example, for speech, from the part of the brain that is related to speech, such that you can have a better, higher bandwidth of communication. Another one, which is very, very exciting, which was released just, I think, last month, is from the Shinoy group in California. And they're using the Utah arrays that I've mentioned multiple times now. But what they're doing is they're not trying to decode where the person wants to move the hand, or where the person wants to move the cursor on the screen, or which type of characters they are thinking of. What they are decoding is the movement of their hand to write the characters. And so what they have come up is with a technology that can allow now, which is the state of the art as of today, to type about 90 characters per minute. And the highest rate from recording from the brain before that was around 40 to 50. So it was doubled today. The fourth and final opportunity that I'm listing here is that we know that artificial intelligence is inspired by humans, by biology. So what if we want to get inspired by artificial intelligence as well? So to use artificial intelligence within our body. And so there are different technologies. I don't want to go too deep into this, but some of the technologies that are done by Jack Gallant in UC Berkeley is recording neural activity from the brain with fMRI and trying and showing pictures to people that are being recorded from the fMRI machine. And what they've come up is this direct connection between what the person is looking at to the actual concept of what's in the image. And as you can see, it's pretty accurate type of technology. And this was already like 5 years ago. And try to connect concepts with actual images that the person is looking at. Another one is the same group is actually then doing the opposite, trying to show a video and pictures to a person in an fMRI machine, and by the signal that is recorded from fMRI, try to decode and to reconstruct from the brain activity what the person is looking at. And so, of course, the accuracy is not that high, but this is already very, very interesting. So what is happening here is they're using machine learning algorithms that are reconstructing and generating the image from a training set that they've had before that. So trying to use images that they have in their training set to then recreate and reconstruct the images that is recorded for the brain, which is, in my opinion, very, very interesting. So we saw the challenges, we saw the opportunities. So what are the directions? We mentioned a few of them, such as Neuralink, but I wanted them to summarize it here. So there are three different approaches in there. On one side, we have closed-loop systems. So the systems that can record from the brain at the same time also stimulate. Examples are for epilepsy, such as the NeuroPace responsive neurostimulator device, which is recording neural activity on the cortex and also in the deeper regions of the brain. And when the epileptic seizure is about to happen, then they stimulate in time with a closed-loop system to then stop the epileptic seizure from spreading. Another technology is a chronic pain by Scalability, which uses similar approach. Another direction, another approach is the bioelectronic medicine field, which is booming now. It's increasing quite a lot. And this field uses implantable technologies, not just like to connect to the central nervous system, so to the brain, but to connect also to the peripheral nervous system and to the autonomic nervous system. Actually, I just realized that I'm running quite late, so I'll try to speed things up a bit. And so this technology can then connect to the nervous system, peripheral nervous system, then to into very tiny parts of the body. The third approach is brain-machine interfaces. We have seen Neuralink, as I showed earlier, which is trying to target the low bandwidth challenge, so to increase the bandwidth of recording from the brain. And these technologies are being developed also by Paradromics, for example, by BlackRock Neurotechnologies, that is being formed together with actually the BlackRock Microsystem company that was already there for a long time. And now they're creating this branch, which is developing technologies for medical solutions, not just for research tools, as they were doing earlier. And then the final one is a synchron device central that I mentioned earlier, which is a very interesting approach. So I wanted to very quickly give kind of like a summary of what's under the hood of the Neuralink technology. And the unique selling points are that they have very small and high channel recording electrodes that they have proven both in rats and mice, I think, but also in bigger animals such as pigs and monkeys. And they showed very recently the video of their monkey, Gertrude. No, Gertrude was the pig. The monkey playing Pong on a screen. There are many other companies. There's a website called NeuroTechX, in which they have summarized hundreds of them into this beautiful, actually, like reconstruction of the whole neurotech world in terms of companies, and also not just companies, but also neurotech hubs and research centers. So I'm getting now to what is happening at our group in London, of the Next Generation Neural Interfaces Lab. So we are a group in which our expertise goes from electronics to biomedical engineering to mechanical engineering, science, physics, data science. And so we are a group of many people that have very different backgrounds. We focus on developing electronic systems that interact with the nervous system and with the brain, and we want to go beyond the current state-of-the-art capabilities. So to have tiny devices, low power, that work without intervention, without external intervention, that have intelligence. So we have artificial intelligence in there, and they are then implanted in wireless. Our philosophy is to develop this neural interface ecosystem and to collaborate with other people. We have a strategy in which we want to be open source and to engage with the public, and also to create commercial translation opportunities. The two main applications are either research tools and tools to help neuroscience to learn more about the brain and the nervous system, and also we want to create technologies that then are translated into clinical practice. This is, in short, our lab. We have different people working in different projects, but they're grouped into five main categories. On one side, we have a neural interface ecosystem, which I'm part of. We have people that are developing microelectronics and microsystems. We have people that are working actually with contactless radar technologies, which is part of another project that we're developing. We have neural signal processing engineers, which are working also with machine learning and AI, and we have people developing research platforms and tools for neuroscience. Our group has been very focused in the past decade on developing electronics and developing application-specific integrated circuits, but more recently we have transitioned into developing technologies that then are used for clinical practice and to develop medical devices from our main expertise that used to be mainly about implementing integrated circuits. We've had different generations of both recording systems and stimulation devices, and the most recent one that was developed in 2017 was a combination between record and stimulation. I want to mention that these technologies are general technologies, so that could be applied and used in different applications. I want now then to focus on two main projects that I've been involved into. The first one is the CANDO project. These projects are developed not just to develop a chip or a device for research, but also to be then in future translated into a medical device. And so the CANDO project is a collaboration between 3 different universities and a hospital, and the goal is to develop a technology, a cortical implant that prevents seizure development in people suffering from drug-resistant focal epilepsy. And so the 3 main approaches are to develop a system, a new concept of system implant based on one central implant and one into the brain with multiple electrodes, developing a technology that can create a closed loop algorithm so we can record signals from the brain when an epileptic seizure is about to happen and stimulate in time to stop the epileptic seizure from happening. And finally, we want to use optogenetics, which is not stimulating with electricity as it is done in state-of-the-art technologies, but stimulating with optogenetics and optical stimulation. But what is epilepsy? Epilepsy is a neurological condition, a disease that affects about 1% of the whole population, world population. And its symptom is the epileptic seizure that is an abnormal activity, an abnormal oscillation of the nervous system that then can translate into into creating issues and problems for people and not having a devastating effect of patients' quality of life. Our approach is to use, as I said, optogenetics. Optogenetics is a technique that was developed about 15 years ago, which allows for cells to be sensitive to light. By doing that, you can then stimulate, so you can activate light to the neurons, such that you can control the neurons by turning them on and off. So by either making them fire more or by making them to stop firing signals. This helps a lot with selectivity and with both spatial and temporal resolution. So you can control better and more specific neurons. And here is the concept that we want to do with the CANDO probes. So, but how does the system architecture looks like? So, as I said, there's a chest implant, which connects through an implantable lead to a brain implant. In the brain implant, there are those that we call optrodes. So there are multiple microelectrode arrays that are implanted into the brain, and then they go deeper into the cortex, about half a centimeter into the cortex, to record and then stimulate. The system architecture is based on the chest implant, which has the energy source, power management, and communication that goes through the wire. On the other side of the wire, there's the brain implant with the optrodes. These are able to both record electrically and stimulate with light. This front-end recording and stimulation then communicates with the data conversion and processing unit, which converts the signals and send it back to the chest implant. In the chest implant, we have the control and processing unit. This is implementing the closed loop algorithm to then stimulate in time on the brain. So to make the whole journey, you record signals from the brain, you convert, you send back to the chest. The chest then is recording and is controlling and processing the recorded signal, and then activates commands that then are sent back to the brain in order to activate the drivers to stimulate with light and to stop neurons from firing, and then stop the epileptic seizure from happening. In the past 6 years, we have developed 7 years now, but we have developed different chips for the brain implant, which we call the optrodes. The first one was based on is actually you can find more information on the paper on the left, and it's based on this particular device that is a passive optrode that is connected to an active chip, and this is the chip that allows to do the recording and the stimulation. And then we developed a chip that then we implemented, and this has 6 possibility to control and communicate with 6 LEDs and 4 recording channels. And here you can see one of the devices that we have developed and create assembly, a multi-optrode assembly. As you can see, we were able to stimulate with light the LEDs. In 2016 and 17, we developed the third make. The second make was actually just testing circuits, so I'm not including it here, but the main difference with this one is that we created something which is the 4-wire communication system, the 4 wicks in here, which allows them to communicate with the chest implant with a custom protocol. Last year, we developed the 4th make, which is what you can see here. We developed a chip that can control up to 16 LEDs per chip, 8 recording channels, has the possibility to have the body potential driver, which will help also with the recording. Chip diagnostics, which we can, so diagnostics is not actually of the biology, but is diagnostics of the chip. So to understand when something wrong is happening within the chip. And also it has, as the previous version, both communication with the 4-wire communication system, the 4 wicks protocol that we have created, and also with the SPI, which is more standard communication protocol. We have created different assemblies and multi-optrode arrays for this, and we are now testing them, both the chip and the technology, and the optrode technology. I wanted to show you very quickly what it means to be part of a multidisciplinary and very complex project. And so this project is divided into 3 work packages. The first one is the engineering team, the engineering work package. The second one is the neuroscience work package. And the third one is the medical work package. And so there are about 40 to 50 people that have been involved in the years into this very complex project. And there are, as I said, 3 different universities and 1 hospital. And this was founded by UKRI, by EPSRC, which is a body here in the United Kingdom, which funds this type of research, and by also Wellcome Trust, which is how it's called, not sorry, it's not coming to me. It's a charity, yeah. It's a charity in the United Kingdom that invests in different types of technologies. The second project that I want to show, and then I will close with this one, is the NGINI project, which aims at developing cortical implants, which are created to have brain-machine interfaces, and so to interact and record signals from the brain in order to control then a wheelchair, robotic arm, or everything that you want. And so this is based on freely floating cortical implants, and is based on this distributed approach, having very tiny, multiple of them distributed on the brain, very scalable, so to go from having just one to many of them, as they have a very small dimension. And we have the possibility with this technology to also record from different depths on the cortex with the microwire technology that I will show soon. So the communication link is based on transcontinuous biotelemetry, which allows for these implants to communicate with a mesh of coils, then will communicate with the outside device that is not then implanted. And so this is the 2-tier communication system that we have developed. And each of these implants has recording electrodes and recording sites at the tips of the microwires that are connected to the main implant. But how does this work? So what we have is a chip scale implant, which is wireless and has an integrated circuit inside of it. So the whole implant itself is a chip that then is closed with the hermetic package that I'll explain later. And the idea is to have an antenna in that chip that will allow them to communicate with the outside world. And here on the right, you can see a picture of our most recent device. And you can see in the middle, there's the integrated circuit and then the antenna on the outside. And in one of our most recent papers, we have then shown how the coupling and how this two-tier powering system works, because these implants use the antenna to also be powered up from the outside. As I said earlier, we have a hermetic encapsulation. So what we want to do is to have a technology which is encapsulated the package such that it is biocompatible and such that it is biocompatible in 2 different ways. So we want to, first of all, encapsulate the technology such that the technology then is not in contact with the body and it's not breaking, so the technology is reliable. On the other side, we want to have this polymer jacket around it, so to make it biocompatible with the body, and so to make the technology not interact with the body to create problems for the body. And so we've created different prototypes, and what we're doing is we're using tunneling connections under the seal ring to have these electrically connected microwires, which, as you can see in there, they are at different depths and different lengths, so that we can reach different parts of the cortex. And we have created different prototypes of the encapsulation and the hermetic packaging. So what we want to do is to record from the brain. As I mentioned, we want to record at different depths, and each channel is in different depth of the cortex, so that we can record what is called the local field potential of each of these cortical layers. And for more technical information, I will then lead you to the paper that we have published. And so what we're having here is 8 niobium microwires. Niobium is an element which we have shown to be very helpful to record LFPs, local field potentials. We have different microwires at different depths and different lengths. We have an adapting referencing to generate a set of multiple channels for LFP recording signals. We are using also unsupervised and ultra power adaptive channel selection for data minimization. So we're using machine learning as well. And we have external processing for our LFP signals that is based on spike detection and spike dynamics. And then on the outside part, there will be a device that then will decode the neural signals that we're recording, then to be used for, will decode the information then to be used for controlling. We have designed different prototypes. As you can see here, we have a couple of them in this slide, and these are biocompatible, and we have different solutions for making the microwires then biocompatible and having the openings of the microwire tips by using this polymer encapsulation. We have also developed 3D printed devices to have macroscopic prototypes then for us to be able to see what it actually will look like, because these devices are quite small. And so, yeah, we've developed that as well. And I want to conclude with something that we have also shown, similar to what Neuralink has presented, is that to be able to make these implants such that they're implanted into the brain, you can't just create the implant itself. You have to create a system that helps with insertion of these technologies into the brain. And so what we have created is a prototype for insertion, which is based on a syringe. And it helps, as you can see on the left side, to put the devices inside and then to remove the insertion device then to create minimal damage for the brain and the cortex. It is a modular insertion device and a method. It is used specifically for microwire electrodes and probes, and can simultaneously decrease the insertion spread and the insertion force when these devices are put on the brain. And so here we have the whole system that was developed to allow for this insertion. We have done some tests and we have published also this work. This is my last slide. I wanted to, actually, so thank you very much for the attention.
Great. I think that's mind-blowing presentation. Thank you, Dorian. I think I have a lot of questions from my side, but before that, audience, kindly can unmute your audio and video and ask your questions directly to Dorian.
I want also to mention something actually before, because I wanted to have a last slide when I forgot to add it. But I wanted to say also that these technologies, as I mentioned already in the discussion at the beginning, are technologies that are done not just for research, not just to stay in a research lab, but they need to be translated. And so one of the our approaches, both in CANDO and NGINI, is that we have created collaborations with hospitals and our research and other research groups in order to translate these devices into medical solutions. And so this needs to happen already at the design stage and the development stage, because it's very important that you are developing the technology knowing that this is going to go into a person's body in future. And that's extremely important also at the early stage.
I mean, that's truly impressive. So I'll just put my first question because I'm very curious about this. So what is the major difference between this kind of design and other sort of RNS and other kind of stimulators that are being present for epilepsy and epileptic seizures? And are you able to get to deeper focal seizures if it is in deeper brain regions? And how far is it effective in that particular case?
So it's a very good question. So what has been done, for example, let's take epilepsy. What has been done so far is that the different technologies have been the vagus nerve stimulation, which is an implant that sits in the chest and connects to the vagus nerve in here. And then by stimulating the vagus nerve, then you're stopping the epileptic seizure from spreading in the brain. And so you can actually reduce the amount of seizures a person might have. Another one is deep brain stimulation for epilepsy, which has implanted in the brain deeper in the region to disrupt what they're called the network dynamics. And so the third then approach is the closed loop system that has been shown by, for example, NeuroPace with the responsive neurostimulator, which is recording and stimulating at the same time for the brain, from the brain, to be able then to break this network dynamics. They're recording because it has been shown that before then the seizure spreads all over the brain and the body, the epileptic seizures start, for example, in focal epilepsy, start from a specific point in the brain where neurons start firing to each other with a synchronous way and synchronous oscillation. So if you are able to detect that in time and to stimulate, to break these synchronizations of the neurons and these oscillations, then it breaks also the dynamic. And so what we're doing in CANDO is we're doing that. We are recording from the brain in the cortex, and we are stimulating those neurons that we know that they're responsible for creating this oscillation to break the synchrony and to stop it from spreading. Many people are going into the direction of deeper regions because for example, in the anterior nucleus of the thalamus, there's a connection of networks that are related to epileptic activity. And so what they do is that with the deep brain stimulator that I was mentioning earlier, you stimulate that part and you stop these dynamics. What we're doing is going directly into the cortex because the cortex is connected to the thalamus. And so we want to break the activity and the seizure already when it starts directly on the cortex, because focal epilepsy, for example, the seizure starts in the cortex.
So can be a replacement for AEDs in epilepsy, or is it just an objective thing just for when the seizure arises?
So again, is it what?
Is it an alternative for anti-epileptic drugs that you're mentioning? Because even, so what is the purpose, specific purpose for this?
Very, very good question as well, because as people know, the anti-epileptic drugs actually work in about 60 to 70% of people, but in 30 to 40% of people, they don't work. They have no reduction of the seizures. And so that's the only way in those people is to actually open up the skull and remove the part of the brain, which is activating the seizure. So what we are saying is that instead of going and removing the part of the brain, which in some patients might be a very functional part of the brain, you can't remove it because it's controlling your arm or because it's controlling your speech or whatever. And so we're saying we put our implant in there and we stimulate and try to not remove that part of the brain, but to interact with the part of the brain.
I mean, that's really impressive. I think that is a problem because even for some patients, as you mentioned, removing a part of the brain depends on age and certain factors. It's really tough for certain patients, and this can be really wonderful. Yeah, I think there's one question from Mr. Mohan R. So,
I haven't
Mohan,
been able to check the questions, but I'm ready.
Mohan, is it possible for you to unmute yourself and ask your question?
Yeah, it's not my question.
Okay, then I'll just, Mohan's question is, optoelectrode systems are fundamentally high power consuming compared to current open or closed loop systems for epilepsy. Given that this needs a power system in chest and connected through neck to the brain, doesn't it work against adoption? DBS systems are moving towards miniaturization. So that's his question.
Give me just 1 second. I apologize. Okay, very good point. So I think what they're saying is that the optoelectrode systems, they use light, and by using light, they kind of like need a lot more power, and that's true. And so that's one of the reasons why we're having a chest implant compared, for example, to NGINI, that it doesn't have a chest implant but has all the implants in the brain. And so the point is that the main part and the more power consumption part of the implant is in the chest. So we have consume more power, so which means that you don't increase actually the temperature in the brain, and the closed loop algorithm is run into the chest. So what we're doing in the brain is that we're using very low power and ultra low power technologies to record and to record from the brain and to convert those analog signals to digital signals. And then we have drivers that are used to stimulate the micro LEDs. And so we're using technologies which are very tiny, and they are not releasing that much amount of light. So they are power hungry, and that's one of the issues that we have been facing of course, but by splitting this system into a chest implant and into a brain implant, we have kind of like tried to mitigate the risk due to power consumption.
Yeah, I think that.
Hi, Dorian. Thank you for such an amazing presentation. My question is like, how do you manage power in the chips? Like, right? And have you tried heat coupling phenomena for that, for charging the chips and electrodes?
Which project you're talking about? Is it NGINI or CANDO or what? The NGINI one?
Talking about the power of chip or electrode be implanted inside our brain. So how do you like charge or give power to those electrodes?
So in the NGNI project, for example, what we have come across before starting the project is that we realized that if you have an implant inside of the brain, the highest power efficiency that has been achieved so far is around 3%. So whatever power that you're giving from outside to the inside, just 3% of it reaches the implant, which means 97% of it is then dissipated into heat, and so there are overheating issues. So what we did is we created this two-tier solution. So we have an outside device which is coupled with a coil under the scalp, so not under the skull, but under the scalp, and then this coil then is connected through ribbon cables with other mesh of coils, which is implanted inside of the skull, so it's under the skull. And this then couples with the micro antennas that are on the implants that were distributed earlier. By doing this, then we have shown that you can achieve about 30% of efficiency. So we are going in one order of magnitude higher efficiency compared to what's out there. And so one of the limitations of this technology is that you still have wires going through the skull. However, all the devices are under the dura. The dura is one of the meninges, which is there are layers around the brain to protect the brain. So whatever goes across the dura, if you have to open this layer of protection, then you might have infections, you might have problems that are caused by this opening. So what we're doing is that we're opening it, we're placing the implants in the brain, you close then the dura, and then you reduce a lot the risk of infection. And then above the dura, then we have the wireless connection that goes with the outside. And so, by the way, I'm saying we're doing this. It's not that we're not actually doing it in human. So this is a concept. We haven't done it yet in human. The idea is to translate that in the future, but this is what we're aiming to do. And we have done tests on different materials to prove this in terms of the coupling. And so what we have shown in our publications is that we can achieve quite a high efficiency. It's still not the best efficiency, of course, because you have layers in the body which are there to protect actually our brain, and so you have to go through biology to be able to for these technologies to work.
Okay. So once charged, for how many hours it works? Like once you charge? As I mentioned earlier, there are technologies that have a battery, technologies that don't have a battery. So the NGINI project, with the brain implants, they don't have a battery. So which means that you are continuously recharging that with an outside implant, outside a device. Sorry, similar to the cochlear implants. The cochlear implant have a device inside and a device outside, which sits. Sorry. Which sits for the whole time close to the ear here. So that's a continuously charging. So there's no battery inside. The same thing with NGINI. There's no battery inside, and there's continuously inductive coupling to power up these devices. Whereas for CANDO, there's a battery in the chest, and the battery is then powering up the devices up in the brain. Okay, thank you very much.
So yeah, sorry, I don't know whether I fully answered, but you asked specifically for how long. There's no battery.
Yeah, you put outer device which can like work with that. Okay,
exactly.
Thank you.
No worries.
I think, yeah, okay, great. Thanks, Deepak. I think there was another similar question, I think, from Mohan again. Are transcutaneous inductive powered systems that you showed, are they same as cochlear implant types? This was the question.
Very similar, yes. There is inductive link, inductive powering, and the difference with cochlear implants in our case is that we are creating, since it's kind of like it's within the skull, we're creating this two-tier system, but the inductive powering method is very similar, yes.
Okay, great. Okay. I think, thanks. The next question is from Ramit. Ramit, can you unmute yourself and ask it to Dorian? Okay, then okay, go ahead, Ramit.
So my question was basically like, what are the ways to like replace damaged electrodes from the implant?
Very good question. Is actually very difficult to replace damaged electrodes. So one of the issues and challenges of this field is exactly that, because once you have placed the electrodes inside, you have this foreign body reaction, and so the brain and the tissue in general creates scarring around this, and it's very difficult in general to replace them. What happens is you just replace the whole device, and then you put a new device with different electrodes. However, these implants are done such that they can be implanted without any replacement for many years or decades. So that's the goal. Since we know that there's going to be this reaction from the body, we know that these devices cannot be replaced every month, of course, also because you need to go through surgery. But one of the reasons is also because the replacement is quite difficult, but not just with our technologies, with all type of technologies, also for the brain stimulators, and they have to remove the actual wire and put a new one, but they are done to stay in the brain for many, many years.
Great, okay. Thanks, Dorian. I think the next question is from Arvind. Can you unmute yourself, Arvind? Hello? Yeah.
Hi, Dorian.
Hi.
You hear me?
Yes, I can hear you.
Yeah. Is there any alternative for the insertions which have been rejected by a compatibility?
Oh, sorry, I didn't quite get. So you're saying alternative for biocompatibility, as you can read in there, biocompatibility failed insertion. I don't fully understand the question. So I guess. So in general, what we do is that we try to make the device biocompatible, and then that's it. It's not. I don't think I fully understand your question. Sorry about that. So, do you mind to kind of like explain it a bit further?
Arvind, do you want to go ahead? So I think so what I thought is maybe if so after insertion, if it is found that the patient the thing is not biocompatible with the patient, so what are the next steps for that? So I think that's what he meant.
I think in general, in medical solutions, what happens is that if there's any issue, then the device is removed, and that's it. There's not much alternatives in general. So it's either if the problem is something that will always be there. So for example, if you put another device, then the problem will appear again. Then you don't use any device anymore. Otherwise, you just replace it with another one.
Got it. Yeah. Okay. So the next question is from Sarkar. Do you want to unmute yourself, Sarkar?
Yeah, sure. So I want to ask that, is there a way to monitor the implant performance after implantation?
Yeah, good question as well. Actually, that's what we are doing in CANDO. So what we have developed is we have developed a system that can record, a system that can stimulate, and what we call it the diagnostic part of the chip. So in there are sensors such as fracture sensor or temperature sensor that are monitoring how the device is behaving while it is implanted. So for example, the fracture sensor, if we know that there's an issue, for example, there has been a movement of the person implanted with the device and the probes have broken,
we're measuring continuously the impedance of this probe of the shaft that goes inside. And so when the impedance change, we know that something might have happened. And also the temperature, if there's an issue in terms of high temperature or there's something going on in there, with temperature also you can detect changes of the device. And so there are these different type of sensors. Another sensor that we have been using into the NGINI project is the humidity sensor. So when you have, as I showed very quickly earlier in the NGNI probe, we have two encapsulation processes. The first one is the hermetic package for the chip inside, and the second one is the polymer encapsulation. So in the hermetic package, you have space between the two parts that are connecting with each other. In this space, we want to put a humidity sensor that can measure the humidity inside, because if the water, so if there's water from the body going inside of the encapsulation, so going through the implant and the polymer encapsulation, through the packaging, the hermetic sealing, inside, then the humidity of the device inside will change. And if the humidity is changing, it means that the packaging has failed. So there's another way to monitor the device, whether the encapsulation has failed or not.
Yeah, so I had one more question.
Yes.
Are there any restrictions which come just after implantation? Like any restriction to normal MRI and all, or any restriction while leading normal lives?
Yeah, that's actually one of the challenges of that us, but also other people have, is that you have to make the technology such that it can be used with current technologies, because having an MRI scan is something common for someone that has a condition such as epilepsy or whatever. And so yes, so one of the challenges in the designing is to make the design MRI compatible. Making the design MRI compatible means that you have to reduce you have to reduce the amount of inductors that you have in the device, such that there's no magnetic coupling with the MRI machine, because the MRI machine has these big magnets. And so, and also in terms of using the materials, in terms of materials that you're using there, you need to be careful in selecting non-magnetic materials. And so that's something that is we had to face. And also something that I really wanted to add as well, which probably didn't appear that much in my presentation, is that in the CANDO project, for example, while designing the device and developing the technology, we're also writing something that's called regulatory file. So for these technologies to be used, you need to be approved in the United States, for example, by the FDA, the Food and Drug Administration. And to do that, you need to submit many documents to the FDA. And in order to do that, you have to write and to show that you have faced all the risks that could happen. And fMRI compatibility is one of them. And so while we're developing these technologies, we're making sure that everything is safe. And we have also, we're checking the risk and to minimize the risk in every type of situation. For example, one of the risks is also, what if the person with implanted the brain is hit by a ball while playing football? And so you have to analyze all the different risks that come with that. For example, shaking, movement of the brain inside of the skull, and so that kind of movement then create an issue. If that issue is happening, what happens to the device? What happens to the brain? And so you need to show all the different analysis that you have done through this risk analysis to prove that your device is used in human.
That's great. Yeah, I think that's a great point. So another, I think, are there any other questions? I think we have one or two questions in the chat that Aravind wanted to ask. So yeah, I think Aravind's one question was, the second question was about the novel materials or the limitations in materials that are being used. And so in terms of material science, what are sort of the game changers in neurotech?
in general, I'm not a material engineer, so that's not my main expertise. But the point is that there's a lot going on in terms of finding the right materials for many reasons. First of all, you need to find a material which is the best one to record the type of signal that you want to record, right? And so if you have a material that doesn't have that property in terms of front-end recording, that's not good. On the other side, you want a material which is somehow flexible, because you want the least reaction from the body. So the more stiff materials that you have inside of the body, the more the reaction from the body, more the scarring tissue will be. However, if it's very flexible, for example, for microwires, if it is very flexible, then it's very difficult to insert. Because as I mentioned earlier, the brain is kind of like a jelly tofu type of material, and it has these layers on top of it, and these layers are kind of like almost as having a sheet around it. So to break the layers is very difficult with microwires that are flexible, or any type of technology which is flexible. So you need to have a trade-off between flexibility of the material and enough stiffness then to be able to penetrate. And so there's a lot of, also in terms of biocompatibility. And so because you can make the whole system biocompatible, but then you have to create those openings for the electrical activity to be recorded. Those openings have to be with metals and other materials that are biocompatible. So there's a lot going on also in our team in terms of materials.
I think that's definitely interesting. So there's one more question, I think, from Mohan. He's asking about the integrated circuits. Are the ICs being manufactured in 13485 approved FAB or in Euro Practice 1?
Yes, so we have, well, first of all, the chips, we have used different companies in the past to fabricate the chips. And what we have used AMS, which is a Europe company that has been doing collaborations with the university, but more recently we have moved to the more well-known TSMC fab in Taiwan, and so it's everything in approved and from Euro practice. So that's one thing. The other thing is that when we receive the devices, these are bare dies, right? And so in order for them to be then post-processed and deposit all the different materials to create the encapsulation, we have our own clean room in-house at Imperial that is has all the facilities then to do the post microfabrication steps to make the device biocompatible and hermetic.
Great. Okay. Yeah, I think those. Okay, great. Okay. Yeah, thanks, Dorian. I think those were the questions that we had, but I have a lot more questions. Definitely, I'll reach out to you.
Someone was asking me for my social. In general, I use quite a bit LinkedIn to share my whatever I'm working on, or to share technologies that are developed there. So you can follow me on LinkedIn. I'm very happy for that. And so you just type my name in there, and then you will find me.
Great. Okay, fine. And I've also posted NTX India's social media handles. So kindly follow or join the group so that you can get updated on the upcoming events. Thank you so much, Dorian. I think that was a very exciting session. I mean, as I always mentioned, the work that you're doing over there on implantable neural interface is really exciting for all of us. And definitely we'll get you back to NTX India's forums or webinars very soon for another session. Definitely. There's a lot more to discuss, and surely our audience will be super excited for that.
Yeah, I hope I managed to summarize a bit, because I tried to put too much material in this time, but I hope I was able to kind of like give a bit of a summary of what's out there and how we fit into that landscape.
Yeah, I think definitely it opened a window on what are the things that you're doing, and definitely it would really help us to go further deeper and sort of research on what things that you're doing at CANDO and other projects. So first of all, thank you so much, and also a huge congratulations, kudos for your work, your next journey on entrepreneurship and things. So thank you so much, Dorian.
Thank you very much.
For this. It was a wonderful session. And thank you so much for all the attendees also.
Yeah, it was really great. Great to talk to you guys.
Great. Thank you so much. Yeah, take care, Dorian.
Bye. Have a nice day. Bye, everyone.
Yeah. Take care, Dorian.